So this video we're going to talk about molecular polarity. Okay, so how do we know when a molecule is polar or not? So in the last video we talked about bond polarity. So like when we're looking at the difference between a carbon and an oxygen, and we're trying to figure out, okay, what's the polarity of this bond? Okay, is it polar? Is it non-polar? Is it ionic? Right? But this time, what we're going to look at is like we're going to look at the whole molecule, right? The molecule as a whole, and we're going to try to establish what's the polarity of the bond of this molecule. All right, and there's really two different types. It's either it's a polar molecule, all right, or it's a non-polar molecule. Now, depending on what it is, it has basically it has its own different properties. It's properties that we could kind of predict. Okay, and so let's go ahead and kind of explore that and see, okay, what's the difference between a polar and non-polar molecule? All right, and so let's start off with non-polar molecule because I think that's the easiest. um Non-polar molecules, there's basically two things that you have to look at. One, all right, the first thing that you need to consider, or I want to say one thing you want to look at, right? So if you notice that all the bonds are non-polar, then you have a non-polar molecule. And this is always true. If you notice that all the bonds between the nuclei are non-polar, then it's a non-polar molecule. So for example, if you're looking at an O2, right, where you have these two oxygens bonded together like this, well, this bond is non-polar. Well, then this molecule, okay, this overall molecule is a non-polar molecule. We know that for sure. Okay, obviously, if you have the same elements bonded together, it's going to be a non-polar molecule. Um, Another thing to look at, and this one, it's you're gonna have to kind of pay attention to this. If let's say if you do have polar bonds, okay, if you notice, right, that if you have the same um, type of atoms bonded to the central atom, and this is big, and there are no lone pairs on the central atom, then in this case you have a nonpolar molecule. All right, so let me give you some examples of what I mean by that. All right, so for example, if we have like CCl4, right? When you're looking at CCl4, you're looking at these bonds, right? These bonds are polar, all right? It's between a carbon and chloride. A rule of thumb: if you have two different elements, for most parts, you could almost assume that these bonds are going to be, there's some polarity in it. But you can always look at the electronegativity values. But these bonds are polar. See, these are polar bonds. So when you're looking at this molecule, it's like, okay, it has 4 polar bonds. But the overall polarity of this molecule is non-polar. Why is it non-polar? Well, there are equal distribution of electrons throughout the molecule, and that's really what kind of sets something that's a molecule to be polar or not. If there's equal distribution of electrons throughout the whole molecule. So when you think about this way, right, you have it where in this molecule particularly, you have the chlorides where it's all slightly negative, all right, and then the carbon is slightly positive, right? And so you have this equal distribution of electrons all in the outside parts of the molecule. So on the outside parts, you have this heavy density of electrons, all right? So there's the symmetry here. And then in the inside, well, there's not so much, all right? But because it's even throughout the molecule, we say that this is a nonpolar molecule. Okay, and so this is the reason why we see this, and almost the same thing from the last example here. When you look at O2, this equal distribution of electrons, it's just being shared equally between these two oxygens, right? And so when you have, as I said, when you have the same type of atom attached to the center atom and there is no lone pairs, because having a lone pair actually really shift the distribution of electrons unequally typically. And you do not have a lone pair, then you're going to have yourself a nonpolar molecule. All right, let's look at another example. So like it's considered like the nitrate ion, right? So let me use a pen and not a highlighter. So the nitrate, so we have a nitrogen here, oxygen, has a double bond. Okay, and so when you're looking at this, we have a different element, the same element, you know, that's attached to central atoms. They're all oxygens, nothing different. It's all oxygens. So you see here that when we're looking at the electronegativities, all right, so oxygen is slightly negative, or slightly more negative in this case. The nitrogen is slightly more positive, all right. But then when we're looking at the distribution of the electrons, it's all more concentrated in the outside parts of the atom all throughout, or the molecule all throughout, okay. And so because of this, we could see and we could easily tell that this nitrate ion is a nonpolar molecule, all right. In of itself, it's a nonpolar molecule. Okay, and that's also because, as I said, if you have the same type of atoms as bonded to the central atom, all right, which creates a polar bond, but at the end of the day, there are no lone pairs to the central atom, then you have yourself a nonpolar molecule. Now, what about polar molecules? Like, what characteristics do we need to look for that will help us determine if something's a polar molecule? Well, so you just think about the same exact opposite of what we saw here, right? If, for example, you have you need polar bonds, right? That's number one. I mean, if you have all non-polar bonds, then that's never going to be the case. If you have polar bonds and you have lone pairs on the central atom, then know that you have a polar molecule. Okay, so like for example, if we have why would we call this a polar molecule? Well, the biggest reason why we call this a polar molecule is because we have this lone pair here. What does this lone pair cause? This lone pair causes an uneven distribution of electrons throughout the molecule. All right, and so there's a kind of like a stronger distribution of electrons here compared to these bonded pair. And so this is what we consider that this right here would be a polar molecule in itself. All right. And another way that we can identify something to be a polar molecule, if you have different types of atoms bonded to the central atom. Okay, and so an example of this is if you have like H2CO, right? H2CO looks like this, right? You have hydrogens here, but then you also have an oxygen here. So you have two different types of atoms bonded to our central atom here, to our carbon. All right, and so because there's difference of electronegativities, right? Like for example, if you think about the electronegativities values, all right, between this oxygen and carbon here, this is slightly more negative, right? While this will be slightly more positive, but this is also but when you compare to carbon hydrogen, it's considered to be a non-polar bond because their electronegativity values are very, very small. It's less than 0.4. So we consider non-polar. All right, and so now we have this, and throughout the molecule, you have a larger distribution of electrons up here, while the rest over here, through the rest, they're pretty much sharing it equally. Okay, and so due to this fact, we say that this molecule is a polar molecule because the electrons are not being shared equally throughout the, or not being shared, or there's not an equal distribution of electrons in the placement of electrons throughout the overall molecule.